Today we're going to study chapter 30, nuclear energy. We're going to discuss nuclear fission and fusion. Now, we studied the nuclear fission. So when a heavy nuclear break up, give you a smaller one, usually we call medium size. What happens? More energy produced. We call binding energy or the fission energy. Because we study in chapter 29, the medium size give you more energy, right? Not a very heavy one, not very lighter one. So we can either combine the lighter one to medium size, we call fusion, or break the heavy one to medium size, we call fission. So this happens first time in 1939, and scientists use uranium-235. Uranium, if you check, we have a periodic table here. Okay, this uranium. The uranium is the heaviest one you can find on the Earth. The most heavy elements. So after uranium, you see this the man-made elements. So we have to prepare those elements. And uranium we can find. So here's what happens. That's 60 years ago. Okay, so now scientists use uranium-235, but 235 has a very long half-life. You see this number here, half-life uranium-235, 700 million years. So of course we don't want to wait. So scientists can make 236. Now see 236, how we can produce. So now scientists use a neutron. Bombard or strike the target of uranium-235. So 1 plus 235 give you 236. So that's how produce 236. Now 236 has one state, which is not a ground state. Has a very short half-life. See the star here means not a ground state, we call excited state. And this state is very unstable. The half-life is only 10 to the power negative 20 seconds. Okay, then has 80%, 85% of a chance to decay. Okay, so now what happens? One neutron join 235, make 236, and 236 gonna break up right away, give you 2 medium size plus bonding energy. Because see the red one's the energy, we call bonding energy. So we call nuclear fission. The heavy one break up to medium sized one and give you energy. Not only that, you see if you add the number, so 94 nucleons, and this one has 140. You add these two numbers, give you 234. But start with 236. What happens? 2 more neutrons come out. And these 2 neutrons are so important because these 2 neutrons can go other target, 235, then make another fission. So 1 neutron in, 2 neutrons out, give you more energy plus 4 neutrons. 4 neutrons go 4 target, give you 8 neutrons, even more energy. So the energy double up. We call the chain reaction. And this is the calculation. So give you the idea what happens. Neutron uranium-235 gave you uranium-236, then gave you 2 medium size. We call strontium and xenon. Then plus 2 more neutrons. Then continue. Okay, so now we can calculate energy. So what is the energy output for one fission? Okay, so this delta M we call missing mass. And here's what we have before, uranium-236. And we can find the mass 236.04556 U. Okay, so then after fission give us these two, strontium and xenon, and also we can find their masses. So this is mass for the strontium, and this for xenon, and plus produce two more neutrons. So minus mass of two neutrons. So this is beginning, we call the parents, and these three we call daughter nuclei. So now the total missing mass, the total mass decrease this much, 0.191232 U. Very small mass, just for one fission. So now if we use the Einstein's equation, how we can calculate energy, mass times speed light and square. Or we simply use 981.5 MeV per U. That's one unit of mass. Give you this much energy. And here's the missing mass times that. Well, give us the answer 178 MeV. That's for one fission. So if we calculate, if we have 1 kilogram of uranium, 1 kilogram, 2 pounds, then we can produce a lot of energy. It's equivalent of chemical energy from 20,000 tons of TNT, or equivalent of electricity, electric energy, which is enough for 500,000 families use for 1 month. Assume every family use up to 400 kilowatt hour per family. So that's about the population of Arkansas. Well, 2 million people, every 4 people in average per family. So that's how 500,000 family. Okay, so from just 1 kilogram, 1 kilogram uranium. Okay, scientists also find other possibilities. Not always. Okay, the uranium-235 gave you the xenon and strontium. Okay, there are other possibilities. This is just another one. Also, neutron joining 235 uranium gave you 236 and break up. Now this time gave you barium and kraton, and then gave you 3 neutrons. Okay, so that's just another possibility. Now, section 2, we discuss a little detail. We already mentioned chain reaction, which is at least 1 neutron per fission, then induce another fission. So you can continue produce more and more energy. And then the critical mass, that's the minimum mass needed for fission. The third one we call abstraction of nuclear fuel. Okay, so now we know when you find the uranium, the mineral. Okay, so you're going to have the uranium-235 and 238 mixed together. And usually it's about 0.7% uranium-235 only. We only have 0.7%. We can use for fission. Okay, so the first thing is how we can separate. Okay, separate. So now the next one for the applications. So we have a nuclear reactor like we have 2 in Roswell, Arkansas, produce nuclear energy. Okay, now the fission must be at controlled rate. You cannot make fission go too fast, double up, every time give you more and more energy. Finally, what happens? Explode. So now you need to have some materials to slow down the neutrons, slows down the chain reaction. So that's very important. So this principal chamber, you see the red one are uranium. In nuclear reactor, in the factory, they only use 3% of uranium. Only 3%, not a very high percentage because too dangerous. And also, they have the special liquid we call heavy water. This is water, but they use deuterium replace hydrogen. Deuterium is the isotope of hydrogen, so can slow down the neutrons. Neutrons shoot each other, produce energy, but sometimes go too fast. So we have a control rod go up and down, when it's necessary. So you can slow down the chain reaction. So this photo here give you from our textbook. You can see inside some rods there. There are a few rods. Okay, and also scientists find plutonium. Plutonium is a man-made element. This one is more efficient, but not available. So we have to make it first. We call breeder. Breeder reactor. So the procedure we're not going to discuss detail. So now this time we can use 238. That's good things because there are more 238 uranium than 235. So we can use 238 to make plutonium. So again, you need a neutron. Strike 238, give you 239 plus a gamma ray. Okay, so now you have 239. 239 going to decay very fast and give you neptunium. Okay, neptunium plus beta particles plus other particles called neutrinos. Now use this one, neptunium, then going to give you plutonium. This is finally what we need. Okay, so that's the how you prepare. And plutonium usually give you more energy, more efficient, and especially for the nuclear bomb, the weapons. So they like use this one, it's more efficient. Okay, so here's the chamber. We do not use nuclear energy directly, and everything happens in the chamber. So then we need a cooling water. So always nuclear plant always has close by big water reservoirs like lake or ocean, because you need cooling water. Okay, you produce nuclear energy, then energy change to the heat, then water start boiling, then can steam, it will steam engine, then produce, okay, so that's nuclear energy to the heat, and then give you mechanical energy, then mechanical energy run electric generator, give you electricity. So the fuel state. So that's how you produce nuclear energy in the principle. Okay, again, inside we have the fuel rods, uranium, plutonium, and we have this go up and down the control rod here. Now after, we're going to have a nuclear waste. The xenons are still radioactive. So now we need to keep them somewhere. So that's the another problem. So that's why we have some social issues, because people don't like the pollution. Now the second application for fission is the atomic bomb. We should call it nuclear bomb. So this one technically is easier. You just need the fission at uncontrolled rate. Okay, so now the fission double up, then finally explode. But again, you have a technical problem. For example, you need a critical size. You need at least, say, 1 kilogram, for example. But you cannot keep them together. You have to separate because together too dangerous. Only when you decide to use it, you put them together, then start the nuclear fission, then finally explode. Now we can discuss nuclear fusion. The definition is joining two light nuclide to make heavy one. So because the heavy one, the medium-sized one, give you more energy. We say heavier one, medium size. We use solar energy every day, but really solar energy is from the fusion, nuclear fusion. Like most star, the sun, like 90% of other star, what we know, use hydrogen, burn hydrogen. Okay, so because fusion need two conditions. First, you need a very, very high temperature, at least millions degree. Okay, and second one, you need high density. Why you need high temperature? Because when you have the fusion, you want to join light nuclei together, right? But they do not like join each other because they both have positive charge. They're going to repel each other, especially when they become closer, closer, closer. The force increase, right? Remember the force equals K times charge 1 times charge 2 divided by R squared. The R is distance between. So when R becomes smaller, the force becomes bigger. Okay, so then how we can make them join each other? So you have to make them temperature very high. Because only if temperature high, so particles go so fast, so they have a chance to join each other. Just like two cars. If they both go very, very fast, they have more chance to, well, the accident. But now we want the accident happens. So you need a very high temperature. And also you need enough particles. So that's why you need a very high density. So discuss a little bit about the what happens in the sun. Is proton-proton circle. So sun use hydrogen. So when two hydrogen combine, give you this one. This also hydrogen, but it's the isotope. Plus one positron. This is like electron, but it's positive charge. So two hydrogen give you the isotope of hydrogen plus a positive charge, and then some particle called neutrinos plus this much energy, produce this much energy. Okay, so now we have this isotope we call deuterium. So now you have another hydrogen combined with deuterium, then give you the helium. The helium, this one's helium should be 2 and 4, right? So this one is isotope of helium. When these two combine, give you the isotope of helium, also give you more energy, this much energy. Okay, then the next, okay, you're going to need two of this, two isotopes combine, now give you the ordinary helium. This helium we see every day, plus two protons, and plus almost 13 mega eV. This is a big part of energy. See that only 0.4, this 5.5, this is almost 13. So this is most important. Okay, so the three step. So we have two hydrogen, give you one of this. Another hydrogen give you that isotope. You need two isotopes. So totally, every time you're going to use 6 protons. Then give you helium and give you 2 protons back. Then totally give you this much energy, this plus that. Okay, so we just need to know the concept. So that's the proton-proton circle in the sun. Consume, use 6 proton and give 2 back. Then here is the total energy produced. So every time give you 24.7 mega eV. That's a lot of energy. So that happens every day, all the time, every moment. Produce solar energy, go all the direction, only very small part come to the Earth. Okay, so we use all the time. Okay, so that's solar energy. So scientists calculated the sun can continue use the fusion energy about 10 billion years. So we don't need to worry about that. But eventually the sun gonna burn out, use all the hydrogen. Okay, so now we're gonna discuss nuclear fusion energy on the Earth. Okay, I want you to remember something. Scientists can make fusion happen on the Earth. They can make fusion happen on the Earth, but very expensive. Very expensive. So scientists can do the research, can make nuclear fusion happen on the Earth, but we cannot use for commercial purpose, not power plant, because too expensive. So that's the something we should remember. We have technology make fusion happens, but not efficient. And scientists have a different approach. Okay, so they use deuterium and tritium, these 2 isotopes of hydrogen. And here's this is very similar to the sun. Okay, use 2 the isotopes, deuteriums, then give you isotope of helium plus neutron plus some bonding energy. Okay, release this much energy. So now this we can find from the seawater. You can find deuterium. But tritium you have to prepare it. You have to make them. You have to make them. Okay, so this 2 hydrogen, isotope hydrogen, give you tritium. That's how I make tritium. Plus 1 proton plus 4 mega eV of energy. So now this time we have tritium. Okay, 1 proton, 2 neutron. Then combine with another deuterium. Together give you helium plus 1 neutron. Then 17.6 mega eV. So this is the fusion energy on the Earth. Again, it's too expensive, not efficient, so we cannot use for commercial purpose. So the same reason, well, you need the very high temperature, you need very high density. So now if we can use the fusion energy, we have a lot the advantage. Here's 3. First is very high efficient. Okay, very high efficiency. You see, compared to the fusion gives you more energy, and also very safe, no pollutions. The final product is the helium, which is very useful. No pollution. Not like fission produce what xenon. And also have unlimited supply from the seawater. Can give you the fusion materials you need. Okay, so the condition is the same. We need a very high temperature, very high density, and also they need long enough reacting time. So that's why it makes so hard. Well, next session really we have some detail how make a fusion happens on the Earth. But this matter we're gonna stop right here. Thank you.